All right, let's start. Hello, everyone. Today is Wednesday, our second lecture for ECE 360 at 1 p.m. And we are continuing our discussion about the control system from Monday. Well, of course, first of all, can you hear me well? Any issues like clarity or volume? Good. Thank you. Thank you for the feedback. All right, we can continue here. Here, I'm sharing my screen here. This is the modules in the Canvas. Obviously, we are now in the module 2, and a little bit about this using of module issue. So you should be able to access the materials in module 2 if you have done reading through these 3 documents in module 1. What I'm saying is the module 2 is locked until you finish the prerequisite, which is module 1 material. So this might be the problem with some of you. If you couldn't access the module 2 materials after today's lecture, and the reason should be the prerequisite. Okay, prerequisite is module 1. Okay, you see here, I'm setting up a prerequisite of module 2. But before completing that, the new module is locked. Okay. Alex, Molly hit the little slideshow in bottom right. What does that mean?
You couldn't see your screen. That's all.
She couldn't see my screen.
I see it now. I'm good.
All right. Good. Sounds good. Very good. All right, we can continue here. So again, this is the how to access the material to in the module 2. Okay. And now let's continue our lecture. Well, last lecture I was asked a question about the specific control system. So I'm figured I give you guys a specific example of a system. Let's take a look at this picture here, down left-hand down corner here. So what this system is obviously you can tell what this is, first of all, what this guy is. What is it?
Probably a DC motor.
It is a motor. However, it is not a DC motor. Okay, this is not DC motor. To be honest, I've never seen this DC motor looks like this. But it's either step or a brushless DC, BLDC. Okay, but anyways, our point is the kind of recognizing the entire system and its constructor. Okay, so this motor is right here is obviously driven by this circuit board, right? This obviously looks like a circuit board. Okay, someone is Molly. Could you mute? Thank you. That's all right. So obviously this motor is driven by this board, and this board connects to another board, which connecting further a third board. So you're seeing 3 circuit boards here. Okay, so let's play a game now. That's just guessing which is which. Okay, first of all, the right next to the motor, and this board, what is it? Anyone have any guess?
Motor controller.
Motor controller. Any other guessing? Any other guessing? Wally's answer is motor controller. It's close, but any I'm expecting any better answer. Anyone? Feel free. Okay, feel free.
Some sort of inverter, maybe.
Oh, very good. I heard excellent answer. I heard an excellent answer. This is a power board. Okay, it's a power board. Now, depending on what type of motor this is, this might be inverter or a kind of other power electronics converter. Okay, so it's a power board. Very strong. Another very strong evidence is what? Can you see this bottom here? What is it? Can anyone see what is this? The bottom here. Heat sink. Very good. I said nothing but heat sink. Okay. So heat sink. Why we are using heat sink? Because we are not using the heat sink for the other two boards. Okay, only for this board. Why is that?
High current generates a lot of heat, so you need a heat sink to dissipate
Exactly.
it.
Very good, very good. Okay, and this is another very strong evidence showing you or telling you or reminding you that this power board is handling very high current, very high power. It makes perfect sense because this power board is driving what? The motor. And it makes perfect sense. And then there's details, of course, how many cables it is providing or say feeding the motor. How many cables? You see that? It's here, right? This is the cable out of the power board feeding the motor. How many cable here? 3, right? That's why my guessing is this is a BLDC, 3-phase synchronous permanent magnet motor. Okay, 3 cables here with different colors, generally speaking, provided by this power board. And another thing you notice is another cable here. Well, the black color is nothing but heat sink or kind of harness. You know what I'm saying? So containing more than one thinner cables inside. Okay, so don't be confused. This is not a single cable. It's not a single cable. The black color is just a harness or heat sink. So this cable, this black one, what is this? Can anyone guess? Anyone guessing?
First guess would have been an encoder, but I don't see enough wires coming out of it to confirm.
Well, very good. It's a correct answer. It is encoder. And it's hard to see multiple small wires like Kevin just mentioned. But however, if you look closely, actually, the multiple wires is over here. Okay, and this is kind of the header. And the female header hook up to the male header on the power board. Okay, this is nothing but encoder. Very good, very good. So obviously, you can tell there's an encoder embedded at the end of the motor here. Okay, encoder. Encoder is feeding back the information like the position and the speed. Generally speaking, it's just a position. Position information feedback to the power board to be controlled. Yeah, very, very good. Very, very good. Okay. So we are seeing the power cable feeding the motor and seeing the motor feeding back the position information back to the power board through this second black cable here. Again, this is just a harness containing more than one thinner, much thinner wires inside. Okay, and then we also see here, right? We are seeing the cable here. What are these cable for? Can anyone tell?
External power supply cables.
Excellent, excellent, excellent. Very good. Okay, obviously some of you have some experience. This is nothing but the DC supply. Okay, this is nothing but DC supply. Okay, without a DC supply, this system cannot work. It's just like equipment without battery. Equipment, your cell phone without battery inside. It's gonna functioning nothing, provide nothing, zero service. Okay, so these cables are DC supply feeding the main power into the power board, as well as the rest of the 2 boards as well. Okay, as the original power supply, okay, for entire system. Okay, that DC bus is providing total power energy, and the inside of this board, of course, you have different DC to DC converter, or say the power supply to lower down that DC bus voltage to different levels, depending upon the DC value you need, right? So very good, very good. This is a very nice game. from where we can basically tell what the system is doing. Now it's a turn for the rest of the two boards. Okay. First, the power board is hooked up to this middle board through what is this called? Ribbon cable, right? Ribbon. Okay. Ribbon cable, multiple wires, okay, in parallel. Okay. So what this board is, the middle board is, what's any guessing? I'm sorry, Noah?
Logic board.
A logic board. What does it mean by logic board? Any more detail?
Like contains the ECU, the controller.
Yep. That sounds much better. That sounds much better. Thank you, Noah. This is actually just a controller board. You can even say. Yeah, you can even say this is a controller board. What is this guy in the middle? This black square guy. What is it? What do you think?
CPU.
Yeah, obviously CPU. Exactly. Okay. The controller board is containing the CPU, the controller itself, which is MCU, DSP, whatever, from different companies, different semiconductor companies, and the peripheral control circuits. Very, very low power. Generally speaking, like what is the current rating? And the current is about what? Absolutely lower or much lower than 1 ampere, right? Yes, maybe 100, not even 100 milliampere. Generally speaking, tens milliampere. Okay, very low current, very low power. Yeah, that makes perfect sense that we are not even using the heatsink or any fans to help the air circulation. Okay, we don't need that. Okay? We don't need extra equipment for heat dissipation. No, it's good. And the controller board obviously is the board connected to where? Computer, right? Everything is connected to the computer to be controlled by computer, right? You're programming in the computer. You're changing the algorithm from the computer, right? Everything is computer work. So you can tell this is the what we call it, D-sub, right? Is the terminal hook up to the computer. Does it make some sense? Okay. And maybe you need another external DC power supply. This board also provides the interface for that purpose. Okay, so this black one, generally speaking, is a DC supply terminal, and you can also see some mail pins, IO pins come out of it. Okay, they're out of actually the CPU, but functioning as general purpose GPIO. Okay, general purpose IO pins, providing PWM or receiving the ADC signal, etc. So obviously the power board is going to provide the feedback, like the position, the signal from the motor to the controller to be controlled. So it's through a ribbon cable here, right? And the controller, of course, also providing what? Back to the power circuit. What signal the controller board is providing back to the power board through the ribbon? What signal? Anyone else?
Duty cycle modulation.
Very good. Modulation. PWM. Excellent. Okay. The controller board is obviously implementing the control through the what? PWM signal. So that PWM signal is going through this ribbon cable with very low power, reach the power circuit, and power circuit has sort of amplification to make the PWM strong enough to drive what? Power electronics switch. Okay, because the switch is the basic element of the power converter. We are saying inverter or any sort of power electronic converter, they consist of switches. Okay, switches is made of what? semiconductor materials, like the silicon in the past 30 years or even 50. But in the near future, the semiconductor dominating the world going to become what? Anyone knows? What semiconductor can dominate? Going to dominate our world. What semiconductor material? Anyone knows?
Silicon?
Like silicon was the past 30 or 50 years. In future, it's already been worked a lot.
Graphite? Graphene?
What is that?
I don't know. I'm just guessing.
No.
Germanium.
No, germanium is kind of a parallel with silicon, and silicon, in terms of many characteristics, is better than germanium. But germanium has low power voltage loss, but still mostly it's in parallel with the silicon. Any other guessing? What is the cobalt? I'm not quite familiar with this term from Sawyer. This is something I'm not quite familiar. But the correct answer is this: is silicon carbide. Okay, silicon carbide and gallium nitride. Okay, silicon carbide and gallium nitride. Okay, I'm typing these two words in the public chat here, so everybody can see it. Silicon carbide and the gallium nitride. Okay, remember these two names because in near future, very near future, everything semiconductor switches, the main component will be made of them. Okay. They have much better performance.
If they change the construction of the MOSFET, does that mean that the calculations are actually going to change as well, or they should be generically the same?
It's gonna be a lot of different, but basic performance, the basic series is same. So, but the details, no, different. Gonna be different. Okay. In other words, learning the MOSFET and the BJT and silicon-based material series remain valid. Okay. And the main difference, improvement out of these two new materials are the performance, like switching frequency and the power readings. And the structures, well, inevitably different in some ways. Okay, this is the a little bit material. We went a little bit too far, but come back to here. I'll come back to here. So this is the controller and the power board. Okay, you need always at least these two things. Okay, the power board itself, you're gonna lose control. Nothing gonna control it. Controller board itself, no, not enough. You can't do the driving thing, okay, because the power is too low. Does it make sense? So high power power circuit and low power controller board, they always work together. Okay, combine them together. Sometimes you might see they're integrated together. Okay? That's absolutely possible. However, it requires more experience and more complication in terms of the PCB making, PCB designing. Okay, you need to separate high power circuit side and low power control side. You need to separate them in the same PCB board. That's possible, doable, however, more complicated. Okay. In my experience, I always separate them. I purchased a control board from a semiconductor company and design a power board itself. Of course, we have the very last, the third green color, and we always use the green color. Okay, even though it's not necessary. Okay. This board, third board. What this board is? Anyone have any guess? This actually, first of all,
base or user front panel board or something like that?
I think close enough. It's optional. First of all, it is optional. Obviously, you have controller board, you have power board. That's enough to drive a motor or any kind of actuator. This board is optional. It's for display. It's for display. Can you see the LCD on it? It's LCD or LED. I'm not 100% sure because I just found this picture online. I just searched it, Google it, and I got this picture. I think it's a very nice, very involving picture. So I make it to be an example in this class. But this is the optional circuit for displaying many indicator LEDs. Okay. Probably I am not able to see clearly, but probably many test points as well, TPs on it, for you to conveniently, to measure the voltage or observe any waveform by oscilloscope. Okay, that's possible too. But generally speaking, the TPs are all around the power board, right? Around the power board. So this is the typical entire system. Now let's talk about our so-called control system. The control system is let's say we design a control algorithm, a PI or whatever advanced control algorithm. Where is it? In this is a system, a hardware, including everything basically, except the external DC supply, right? This is a complete picture of the entire system. So where is our design algorithm? Where is it?
Stored in a micro.
Exactly.
Micro's RAM or whatever.
Exactly. Yeah.
Storage device.
So, yep. So keep this concept in mind. Like I said, the controller board is connected to the computer, right? In a computer, you have a software programming environment. In that environment, you're programming your controller by C or C++ or embedded C. Nowadays, the language for microcontroller is mainly the embedded C, so-called embedded C. Okay. And then you program in the computer, right, by a keyboard, and then those programmed code, the algorithm, gonna be compiled and executed by the CPU over here to generate a PWM signal and then feeding the power board. Okay, feeding the power board. So this is how we control algorithm kick in to the system. And some students ask me, is the control system a hardware job or a software job? I will say it's both. I will say it's both. In terms of the hardware, you might want to learn a lot of other things, power electronics especially, the circuit design especially, and how to use the PCB design, etc., so that you are able to design circuits. And software-wise, it's mainly unfortunately, maybe is quite theoretical, mathematical algorithm design, and then you need to learn how to program them in embedded C language. Okay. Those are part of the software job. Okay. So here I'm showing you zoomed in. Well, it's not exactly the same thing. However, I'm just give you a zoom in picture. Also, the picture, different pictures I got from the Google. Okay, controller board, as I said, this up is hooking to the computer, and of course the debugger, it generally speaking is JTAG. You see this JTAG, these male pins. JTAG for debugger, connect to the debugger, and then you have a power supply. Maybe you need a power supply, 9 volts, 12 volts to this guy, And maybe the controller board itself has an LCD display. That's very helpful too. And here you have a very small part of the space for vector circuit design. You can wiring jumper something over there. And this is the CPU, or say the MCU, the DSP chip itself. And I have a guess. Well, what is this? Anyone knows what is this? This black one, black socket, right? Can you tell this is the black socket? What is this for?
Input, output.
Very good, very good. Yes, close enough. And here we are seeing a ribbon cable, male header to connect to the male cable, ribbon cable. But here you're not seeing one. So you can easily tell this board is not really this board. They're not same, okay? But different design, same feature, same concept, same idea, but different from different companies. Okay? So this is a socket. You can insert a kind of I/O board from where you can access the I/O pins. Okay. So there's some buttons here for different physical analog inputs. Okay. And this is the typical encoder. Obviously, again, not the same thing here. Okay, they're not the same thing. I'm just give you example encoder here. And from where you can receive the position information. The encoder is nowadays we always use is what QE. Q represent the quadrature encoder. Okay. So this is what. Well, this is what. Anyone can have any guess? What is this? LEM. Probably you ever use this. This is a very popular company, manufacturer of what? Anyone knows?
That's for current measurement.
Very good, very good. I received the correct answer from Alex. This is a current sensor. Okay, this LEM is a very popular, very famous current sensor manufacturer. Okay, this is a current sensor. You can guess this is very easy. Right? Where the cable goes through this hole, right? This rectangle holes. You make your current containing cable going through here, and then it generates certain proportional or linearly related analog voltage signal out of these pins, right? This makes sense. And then give this analog signal to the controller, A to D. So to be converted to a digital signal, to be manipulated or processed by the controller, right? So this whole is very meaningful. It's very meaningful. You make your wire going through it, and then you receive the analog signal correspondingly, accordingly. Okay. These are hardware, some pictures. So also leading you guys to go through some typical examples to know where we at actually, okay, where we at. And here, the programming is the software job. You need to learn how to program the CPU, the microcontroller. I think if you guys have already taken the 355 or embedded system course, you should kind of understand better what I'm talking about here. But if not all of them, that's okay. That's okay, right? Right. This is a typical example of system, including the control system. Actually, including the control system. And so, it's a system always consists of hardware job and the software job, and then the knowledge you learned, how it kick into the system, it's actually is up to different subjects you learn. Yeah, it's up to a different subject you learn. Okay. Any questions before we move on to our actually, according to this scan chart, we are here. Before starting the module 2 frequency domain modeling, any questions? All right, let's go ahead. What I'm gonna do is, again, real-time writing notes. Okay, real-time writing the notes, and hopefully so could you. Module 2. Frequency domain modeling. Frequency domain modeling. First thing we want to talk about is this. What we do in this module, of course, in this subject. What we do. What we do is simply can be explained in this way. Let me know if my handwriting is blur or you don't understand what I'm writing here. Okay, let me know. I will read through. What we do is simply explain it like that. We begin with real physical system or component. And then we're gonna somehow describe the system or component by what is DE? What is DE? The prerequisite of this class, right? Differential equation. Okay, DE means differential equation. This is the most straightforward way to describe a given physical system or component. Okay, remember, so far we don't know any other better method to describe, accurately represent a given physical system or component. Okay, only differential equation. Okay, differential equation is the best way so far, okay, to describe the input and the resulted output, or say the system behavior or component behavior. Okay, the best way is nothing but differential equation. Okay, so after taking Math 262, you should have a conclusion that what we learned this differential equation for. What is for? What is it for? For describing whatever you're gonna learn in your engineering system. Okay, you are able to model it. This is nothing but modeling it. Okay, modeling it. However, in this course, the module 2, frequency domain modeling, is not mainly dealing with this part. Is mainly dealing with second part. How we convert the available differential equations, plural, to S function. What does it mean by S function? It's nothing but the term we learned on Monday, transfer function. Okay, transfer function. How we do this conversion, okay, is our job in module 2. Job in module 2. Differential equation is in terms of time at t. Does this make sense? It's a function of t. Okay, your derivative with respect to t, generally speaking, at least. Okay. S function is what? In terms of s. Of course, that's why we call it S function. Okay, so transfer function is in terms of s. Differential equation is in terms of t, is of t. Okay. So first of all, this is the first thing you need to know. Second thing is this. I'm changing my color. Let me ask you a question. From a given system or component, how you come up with the differential equation? In other words, what's the way? What's the medium you based on to come up with the differential equation? Say I have a pen here, right? I give you some force and roll down. How long the distance are gonna roll, and how much force I give, they're related, obviously related. So how can I come up with a differential equation to describe this behavior, this what happened? U based on what? Here. Anyone? Anyone have any thought? Anyone, any thought? It's okay. It's okay. It's actually physics, right? Well, it's absolutely making sense if you have no answer. I mean, we are engineer students, right? So it's absolutely normal. Okay, this is nothing but physics. Physics principles. Okay, we have to give enough credits to to the people who work on or doing research in physics and math. Okay, they are really the basis of engineering. They really are. Okay, the physics principles are the ones we based on to come up with differential equations. Okay, it's not out of nowhere. Okay, it's not out of nowhere. Okay. The second step, which is our main duty in this module, is how we got the S function, transfer function, from the given differential equation. What we do is, we mentioned this a little bit last lecture, Laplace transfer. Laplace transfer. Laplace transfer. Oh yeah, Sawyer provided the correct answer. I just saw it. Well, that's why I recommend you guys to use microphone, right? Sawyer was right on this. He figured it's physics. Exactly, physics. Okay. So differential equation to the transfer function, we need Laplace transform. Okay. And also what we're gonna do is the other way around. As you know, we're gonna do inverse Laplace transform. Okay. So this is clearly explaining what we're gonna do. Okay. Now let's talk about details one by one. First, let's learn some physics. Not learn. You should, to all of you guys, it's supposed to be reviewing. Okay. Even though the physics 212 is not a prerequisite, you should know some very basic ones. For example, everybody know who this guy is, right? He deserves it. Okay, trust me, he deserves it. Okay. Newton's law. Newton's law. I don't know how many laws he has. He developed 3, right? 3 laws. And the one we really use a lot is the second one, right? The second one. If we just talk about the second one only, the second one is what? Be careful here. Actually, there are 2 versions in second law. Right? 2 versions. It's not only one. The first one is this, right? What is it? Net force equals to what? Mass times what? Acceleration. Acceleration. Sorry about the rusty spelling, but this is what I got. Okay. And acceleration could be further expressed as this, right? Derivative of what? Velocity, right? Velocity. Right? And the velocity could be further equals to what? Derivative of what? Displacement. Displacement. Velocity equals to derivative of displacement with respect to time t. Therefore, it equals to m times second order derivative of displacement with respect to time t. Doesn't make sense. So it is involving the mass, accelerations, velocity, and displacement. Okay, this is one version. This is only one version, as I said. Second version is this: not net force, but net torque. Okay. It's not mass anymore. It's J times acceleration. Who is J, by the way? Anyone knows? Who is J?
Energy.
Very good. Inertial, right? Is inertial. Very good. Okay. Is inertial. And acceleration is not equals to derivative of velocity anymore. It's equals to what? Well, by the way, what's the difference between this two system? The first version of the equation is describing what kind of system?
Linear versus angular.
Very good. That's close enough. We call it what? Translational, right? Does this make sense? This term, translational. Second is what? Translational is basically linearly moving. The second was what? This is not force anymore. This is torque, right? Equals to inertial times acceleration. This is what system? Rotational. Rotational. Rotational system. Okay. So that's why we have two different versions. Okay. So to rotational system, the acceleration is not equals to the derivative of the velocity, or say. It's not the horizontally moving linear velocity. What is it? What velocity? It's still velocity. What is that?
Omega.
Omega. Excellent. Omega. What is it? Two. What is it?
It's the angular velocity.
Excellent. 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 Good job. Okay. Angular velocity is a rotating system. Very good. Very good. Okay. And the further this velocity, angular velocity equals to a derivative of what? And therefore, second order derivative with respect to time t. So second order of what? Angular velocity equals derivative of what?
The angle or theta. Yeah.
Exactly. Yeah. Angular what? Angular position. Okay, angular position. Angular position. Guess what? This guy is nothing but the guy feedback by the what? Encoder. Remember? We just mentioned this. Okay, from the real system we just saw. The angular position out of the encoder is nothing but theta. Okay? Well, to be honest, it's not directly the theta, but it's actually providing the theta. Okay, it's not directly. There's a conversion between the theta and the signal provided by the encoder, but we won't go that far. Okay, so this is Newton's law, second law, actually. Okay, what here? My bottom line is what? Is what we see here is nothing but differential equation describing the movement and the force. Does it make sense? This is nothing but differential equation. Okay, differential equation. The next one, let's review more physics. The second one, let's talk about the passive component. IV characteristic curve. Okay. By the way, what does it mean by passive component? Passive electric component. What are they? Anyone? Or let me ask this: do you guys know who is the typical active component, electric component? Who is the active one? Anyone? The typical active one is
transistor.
transistor. From Connor, right? From Connor. So I think Jeff just mentioned this correctly. Passive components we are talking about are LOC. Active component, the typical one is op-amp. Okay, it's op-amp, operational amplifier. Okay, op-amp, which we're gonna play with a little bit tomorrow. Okay, we're gonna play with. Oh, I'm sorry. I'm thinking of 318 lab. I'm sorry. To some of you, we're gonna play tomorrow. Okay. Tomorrow we have a 318 lab, so in where we're gonna play the op-amp. But passive components, we always talk about RLC. Okay, RLC. What are the physics principles for them? Nothing but the IV curve, or say IV characteristic curve. Of course, here we don't have to really plot it, but mathematically, the equations is the differential equation we can use to describe the behavior of these passive components. To R, it is what? It's very simple. It's just Ohm's law, right? It's just Ohm's law. Just simple as this. This equation, I know you're not seeing any integral and you're not seeing any derivative. However, this is nothing but one type of differential equation. Okay, it's one type of differential equation. We got an accurate model differential equation. To L, the voltage across the inductor equals what? Anyone remember this from circuit 1 or 2, whatever? Better. Anyone remember? Voltage across the inductor.
IDV no, that's
I L D I dt. Good. That's correct. Very good. Yeah, very good. Very good. Okay. This is the inductor. And to the capacitor. What is it? Sawyer, can you speak loudly? Loudly.
I think it's C and then the integral of the current with respect to time. Is that correct?
That's very close. That's very close. The only mistake is here is 1 over C.
1 over C. Okay.
Yep, 1 over C. Very good. Very good. Okay, very good. Abbas was right, basically. Okay, so this is the IV relations. Of course, here this is you can do a little bit changing here. You will see different format, but it's pretty much the same equation. Okay. Pretty much the same equation. This is what we learned from circuit basic. They're nothing but differential equations. Okay, these are all differential equations. What else we can have? We can come up with the differential equation or equations. Never forget KCL, KVL, okay, and other circuit analysis skills. Okay. What I'm saying is, given the, let's say just as not a mechanical system, but the electrical system, electrical circuit, we want to have some equations to model this system or describe the behavior of the system. To come up with equations, right? How to come up with equations? Never forget the KCL, KVL, those circuit analysis skills. Those are basically we can depend upon. Okay. So KCL, KVL, absolutely, absolutely. All right. These are the physics we use very often. There's of course some other physics principles we need as well, but here we don't need to list all of them. And next, let's talk about Let's talk about what? Let's talk about Laplace transform. Laplace transform. Mathematically, it's actually quite a complicated thing. First, please become familiar with such writing. What I'm saying is, here, given a time domain equation, or let's say just a time domain differential equation in terms of t, we are applying Laplace transform on it. Okay, so this is trying to do this. This is how you interpret this. You mean this?
Oh, never mind. You're at the bottom. I thought you were writing under it.
No, nothing. Yeah, that's the bottom. Yes, that's the bottom. Okay, so you applying the Laplace transform onto this given time domain differential equation, and then you are receiving the S domain, or say frequency domain model, which is S function, or say the transfer function. Okay, this is the differential equation. This is the transfer function. Okay, this is the basic idea. A lot of details, we will see examples, but now this is how we interpret this behavior. Okay, just get familiar with this writing. Mathematically, it's like this. Okay, it's quite complicated math. It's integral from 0 negative to infinity. What does it mean by negative here? 0 negative means what? Means the moment right before the 0. Means the moment right before the 0. Okay. We will see if any examples, but now we just mentioned it. Integral of the function of t times the exponential function, e to the negative s times t. And of course, s here is a complex number. It's a complex variable. Maybe you see in future. Okay. So mathematically, it's quite difficult. It's quite complicated. But we have a transform table to use. Okay. So if you took some other courses, you might have used that. Okay. We generally speaking don't need to apply such complicated math to find the Laplace transform, but it is there. It is there. And obviously, the next one is the inverse one. Laplace transform. Right. The other way around. What do we do to implement the other way around? First of all, this expression is very meaningful. You need to understand. So, which means you given a transfer function in S domain f, capital F of S, you're applying inverse Laplace transform operator, kind of operator on it, and then you end up with a time domain differential equation, lowercase f of t. Okay, and mathematically, even worse. Okay, it's like this. Okay, it's the integral of from lower delta minus j infinity to delta plus j infinity, and then of this transfer function f of s. Okay. Also, we have inverse Laplace transform table to use. Okay. Generally speaking, we don't have to go this far. Okay. And now let's show some of the handouts. This is one of the handouts. Actually, we have two for this lecture, and one is the Laplace transform table, helping you to conduct the both Laplace and the inverse Laplace transform. Another one is theorem. We're going to use it later. So first one, let's take a look. This is something probably many of you have seen before. What I want to emphasize are the first four, because they have name. They have name. First one is a particular signal. We call it impulse. Okay, impulse. Impulse signal transfer the function in time domain is a constant a times delta of t, and corresponding S domain transfer function is a itself. Okay, a is a constant, or you can imagine or you interpret it as the amplitude. Okay, amplitude. Step function. This is the most popularly used signal as the system input for testing. Step input in time domain is just a function. It's a constant. It's just a constant, a, with magnitude of a. Corresponding S domain transfer function is a over s. Okay. A little bit more about the step function. The step function. Okay. Impulse. What does the impulse function look like? Just add t equals 0, you have a pulse. That's it. And the peak value is nothing but a. If we have amplitude a in front of the delta. If a equals to 1, that's a unit impulse, unity impulse, right? Then what does the step function look like in time domain? We're now talking about the time domain graph. Okay, visualize how you visualize the name of it. Okay. Step. What does the step a look like? Before t equals 0 is 0. From t equals 0 on, you have a constant a. Flat line, constant a. Okay, just simple like this. It's a what? It's a step up. Okay. So it's not, so a constant a is not a 100% accurate description. It's actually a step. T equals to 0. Let's start to have a value of a, and then forever. Okay. Before that moment, okay, there's nothing. Makes sense? This is how we understand this step. Going back to here, the third one is so-called ramp. Ramp is constant, or say amplitude a times t. Corresponding transfer function is a over s squared. S squared. And what does the ramp look like? Ramp looks like this. Is a times t. What does it look like? Again, before t equals 0 is 0. From t equals 0 on is a ramp. What's the slope? What's the slope? A, of course a. Right? Slope is a. Okay. This is so far we are trying to visualize the signals, okay? Because now we are talking about signals. Okay. Because we're talking about signals. 4 typical signals we're gonna play with through this semester, especially the second step. The last one is called parabolic. parabolic in time domain is half a times t squared. Again, a is functioning as an amplitude. In corresponding S domain, or say frequency domain, transfer function is a over s cubed. Okay. Now, what does it look like in time domain then? This is maybe you guys know this even better than the previous form. Okay, that's parabolic. What does it look like? This is a times t squared. What does it look like? Right? That makes sense. I'm sorry. Yeah, I supposed to use the red, okay, to keep consistency. Right. This is a parabolic. Okay. So this is how we visualize the signal, and here as a corresponding Laplace transform. Just be careful. Here we have a coefficient of half for a parabolic, and here we don't. So be very careful. Be very careful. This is a place where very easy to make mistakes. Obviously, right? This is the one of the handouts we're gonna use quite a bit. Now let's talk about the second thing. All right, we are done with the Laplace transform and inverse Laplace transform introduction. Okay, now let's talk about the next thing. Now we start to really do it, really conduct the Laplace transform and the other way around. Okay, let's now talk about from differential equation to S function. This is one way. Remember this one. I'm talking about nothing but this, the top one, followed by the bottom one, of course. So now we are talking about the top one, from differential equation to S function. What we do is just the Laplace transform. Okay. How to conduct Laplace transfer. Two equations. Okay, two equations, not only one signal. Okay, there's two equations. Let's see how we do it. Okay, let's see how we do it. The first one, let's defining a generic differential equation. Okay, order of this differential equation is obviously is n. Okay, sorry, a link C of t to be n. So the function here you're seeing is C of t and R of t. Okay, C, T, R of t. By the way, from the understanding of the differential equation, what do you think? C and R are respectively are what? If we are considering this as a generalized the generic differential equation, C of t and R of t respectively are representing what? Can anyone? Any guess? To a system. You're describing a system, right? Describing a system. So the C and T are respectively what? They both are a function of time t. Okay, don't be confused. Differential equations still in terms of t. Okay, their derivative with respect to t. Okay, remaining that way. However, we have two signals, or say two variables, c and r. What are they? Anyone? Any guessing? None? All right, that's fine. One is input of the system. The other is the output. Okay. Of course, it might be the other way around. This one is output, this one the input. It's all depending on how you define them, right? It all depending on how you define them. So one is input, another is output. Both are in terms of time t. Derivative, the differential equation are like a input derivative to t somehow related to output derivative with t. Okay, this is the generic differential equation describing a given system. Okay. So now what matters is what is the result of Laplace transform on this generic differential equation. And now let's just define. Let's define. Oh, like I said, just I'm defining it from my notes the other way around, but that's okay. Let's define input as R of t, output as C of t. So I need to change here as well. Out of t. This is the input. All right. It's all depending how you define them. That's not a big deal though. So let's just define R of t as input, C of t output. And then we're going to conduct the Laplace transform onto this equation. How to conduct this Laplace transform? Well, first of all, we are observing actually on both sides of the equal, you are seeing the summation of bunch of terms, right? So we can conduct the Laplace transform on each term and keep this summation. So what we do is conduct the Laplace transform one by one. So first term is this guy. First term is this guy. A sub n times dnc over dtn. Right? So what is the Laplace transform of this guy, this term itself? What we need to do is go to the handout, the second handout. Look at the number 9. Look at the number 9. Laplace transform of dnf over dtn equals to what? S to the n times f, which is capital F of s, minus bunch of terms in terms of what? Initial value. Okay, 0 minus here, they're talking about initial value. F function with k minus 1 order of t equals to 0 minus. It's nothing but initial value. Okay, so according to this, and if we are assuming 0 initial values of RT and CT, then what is the result of the Laplace transform of this guy? How about an s to the n capital C of s? Does it make sense? I'll give you guys a kind of 20 seconds to think about this. Laplace transform of this guy on, and then end up with this. Let me see how you same time show both. There you go. Look at number 9. Look at number 9. From this guy to this result by applying number 9. Any questions? All right, if this is clear, then the rest are what? The second is this term, right? This term. And then what do we got? n minus 1, right? S to the negative n minus 1. And then capital C of S. Right. Need to remove this down here. Does it make sense? This is second term. And so on and so forth. And to A1 derivative of C of t. And then what we should got? A1 S itself, C of S. Right. And how about the very last term? A0 times C of t. What is the corresponding Laplace transform result? What is it? E0, capital C of S. Does that make sense? We're going to do the same thing to the right-hand side of the equal. And then we're going to end up with, oh, I'm sorry. Here, there's a small glitch. When we label the other hand side of the equation, differential equation, we want to use the subscript of m, not n. I'm sorry about this. Trying to differentiate from the left-hand side of the equation, even though it's okay, but here, of course, dm. dm. This m minus 1, this m minus 1, 2. Does it make sense? Again, it's just for differentiating from the left-hand side. Okay. So therefore, according to this table, again, one more time, so this result is going to be bm s, the m now is not C anymore, but R, and the capital, right? Capital R. Then plus bm minus 1 s my m1 minus 1, capital R of S, and then plus b1 s R S plus b0 capital R of S. Does it make sense? Any questions? This is how we conduct the Laplace transform on a given differential equation. Any questions? All right, if this is clear, then we still need the second step, okay? Applying the Laplace transform is just the first step for us to find out what the S function. We still have the second step. Second step is to find the transfer function. S function means nothing but the transfer function. And if you recall the transfer function definition we learned from Monday, the transfer function equals what? The output over the input, the output divided by input. We know the output is whom? C. We know the input is R. So the transfer function, we can define the transfer function as like maybe H of S. Right? The transfer function between input and output, we define it as H of S, and it equals to output C over input R, both in terms of S, of course. And then what we need to do? Just combine the coefficients of C and coefficients of R, and then do a division, right? So what's the numerator? Going to be polynomial, right? The numerator is what? Anyone? It's a polynomial of S, right? What is it? You can begin with a little bit, and then the rest of the thing we can follow. What is the numerator? Polynomial.
an to the s, or an times s to the n plus an minus 1 times s to the n minus 1.
Close.
Continue down.
Close, but any correction? Because we are talking about numerator. Anyone?
It's the BM.
That's good.
All
Good.
B.
Very good. Very good. Okay. So be very careful. Okay. All of you guys need to be very careful when you do this in the exam. Okay. It's backwards. It's backwards, right? So numerator is supposed to be m. As to the m, right? Must be m1. M minus 1 plus etc. Plus b0. So the numerator is actually in terms of the coefficient of r. The denominator polynomial is in terms of the coefficient of c. Does that make sense? So be very careful in the exam as well. Right? This is the result. And obviously how we come up with this different transfer function is how the procedure is much more important than this result. This result is useless. Okay, this result really useless. How we come up with it is the entire procedure. Not very complicated, but you want to know how to do it. Yeah, so that's you can get good graded exam, right? So this is how we begin with a given differential equation, and then you go through Laplace transform, and then organize into a transfer function format. Okay. So this is basically the one way. Remember, this is just the one way. Okay, from differential equation to the transfer function. Okay, we have the other way around. Okay, which gonna be instructed next Wednesday, right? Is that next Wednesday? Yeah, I think so. All right, any questions? Right. Here, basically everybody is here. Yeah, everybody's here. I want to ask a question. So, on Monday, I'm planning the exam time to be on the same as the lecture time. However, the point is, if I give you 90 minutes plus 15 minutes, end up with 105 minutes, those time lengths for the exam, is it going to affecting your right next lecture? You understand what I'm asking? Is it an issue to anyone?
Whoa.
For 341 starts at 4 o'clock. And after
I wouldn't mind that time.
Okay. Because 341 shouldn't be a problem right now.
No
What
one
I'm-
means.
What I'm saying is that we have a class directly after 341. A lot of us in here, so.
Oh, you're talking about 341. Yeah, the
Yeah,
same
yeah.
number there. I see. I see.
But no, this
I
one
see, I
should be
see.
fine, at least for me.
I see. So 360 might be okay. 341 gonna be all right. Thank you too. Thank you, Elliot, for this feedback. Thank you, Wally. All right. So 341, I'll figure out something else. Okay, maybe. Oh, so you guys have some classes like starting at 5:30. Is that?
Yeah, a lot of us have computer engineering.
Oh, I see. Then there has to be changed. It has to be changed. Otherwise, has to be. Yep, I figured that out. 341. Okay. So, but 360, this class, no one has any issue. I'm not receiving any issue report. All right, if everyone is fine, okay. Kevin said, no issue with overlapping for my classes. Oh, there's no overlap. Or no overlapping, right? You mean there's no overlapping? Okay. All right, hopefully. All right. Thank you for the feedback and attending today's lecture. And if extra feedback or questions, please shoot me email. Otherwise, see you guys next Wednesday. Okay. Thank you. Bye. Yep, sure, no problem. Bye now.